In this lecture, we will move on to the next topic, and that is the cooling load estimation. And when we talk about air conditioning, we can divide air conditioning into two broad categories. One is comfort air conditioning, and the other is process air conditioning. We will talk about those later on, but right now when we talk about comfort air conditioning, it is for human comfort. And before I move on to the cooling load estimation process, let's talk a little about what it is meant by thermal comfort. A thermal comfort is largely a state of mind that is separate from the equations for heat and mass transfer and energy balances. But however, the perception of comfort is expected to be influenced by the variables that affect the heat and mass transfer in our energy balance model, that is the energy balance model for a human inside a conditioned space. And the factors which are of importance are the air temperature, the radiant temperature, the air velocity, the humidity, the type of clothing a person is wearing, and the type of activity that person is engaged in. Based on a large number of experiments that have been performed over many years, Ashrae has developed an industry consensus standard to describe the comfort requirements in buildings. That standard is known as Standard 55, and I will show you the graphical representation of that standard. The purpose of this standard is to specify the combinations of indoor thermal environmental factors and personal factors that will produce thermal conditions which is acceptable to a majority of the occupants within the conditioned space. The perception of comfort varies from individual to individual, so it is not possible to satisfy each and every person in a conditioned space in terms of thermal comfort. So we have to work on a statistical basis, and if we say that 80% or more of the occupants feel comfortable, then those conditions are acceptable. I will now show you the Ashrae Standard 55, which is a modified form of the psychrometric chart. So I'll bring it up on the screen and then I will discuss it with you. Now we can look at the Ashrae Standards 55, which is, as I said, a modified psychrometric chart. You can see the humidity ratio on the vertical axis on the left hand side. Instead of the dry bulb temperature, what you have is an operative temperature, and the operative temperature definition, I'll come to that shortly. And on the right hand side on the vertical axis, it's not shown over here, but we have the dew point temperature. Then you can see there are certain other numbers shown over here. Of course, you have the relative humidity, but two other numbers we can see, 1.0 CLO or CLO, and the other is 0.5 CLO or 0.5 CLO. And the Ashrae comfort zones are defined for summer as well as winter air conditioning. And you can see that I have marked out a zone by a red boundary, which is the zone for winter air conditioning. I'll just put the letter W over here. And the other one is for summer air conditioning. and the boundary of the two zones overlap over a part of the graph over here. You can see that the winter air conditioning zone, which is shown by this red border, is shifted towards lower temperatures, whereas the summer air conditioning zone is shifted towards higher temperatures. And the reason is based on the clothing that we wear during winter and summer. Now these numbers 1.0 CLO and 0.5 CLO refer to the thermal resistance of the clothes that people would be wearing in winter and summer. So CLO is nothing but another unit that is used in the air conditioning industry to represent the thermal resistance of clothing, and you have a conversion between CLO and the thermal resistance, which will be shown to you, or it's given to you, and when we move forward you will see that conversion factor. So in winter we wear clothes which have a higher thermal resistance. So even if the temperature is, ambient temperature is lower, you will not feel uncomfortable. So that's why the winter comfort zones are shifted towards lower temperatures. In summer, on the other hand, we will be wearing clothing which is light, that is, it has a lower thermal resistance, and if the temperature drops too much, you will feel uncomfortable. So you feel more comfortable in a zone which is shifted towards higher temperatures. So we can, depending, because it's the comfort level is a mental perception, you can have a person feeling comfortable at various points in the zone. So you don't have to limit yourself or define the comfort conditions at a particular point, but there's an entire zone, and depending on a person's or a group's perception of comfort, they can be at various points within the zone. I will now come to those definitions and the conversion factors. Now this comfort zone definition, or standard 55, is for certain conditions. One in which the air speed in the environment is less than 0.2 meters per second. The resistance of the clothing that people are wearing, that is also given, and the activity level is less than 1.1 MET. MET again is terminology that refers to the rate at which heat is generated within the body due to the metabolic activity. So you can convert a MET into units of watt per meter square, and those units are given over here. A MET is 58 watt per meter square, and similarly, as I said, 1 kilo can be converted into units of thermal resistance. 1 kilo is equal to 0.155 meter square Kelvin per watt. Then we come to the term operative temperature, and once we have defined or understood what operative temperature is, we can also define radiant temperature, which was given earlier, along similar lines. Now if you consider a conditioned space, just consider a room, it will have walls, you will have a ceiling, you will have doors, windows, and those surfaces will have different thermal characteristics. When we talk about thermal characteristics, I mean the characteristics like emissivity, absorptivity. So when you talk about radiation heat transfer, these are surface characteristics which are of importance. And those walls, the ceiling and surfaces will be at different temperatures. And if we have an occupant in that space, he will or she will be exchanging energy with the surfaces by radiation, and that occupant will also be transferring heat to the surrounding air by convection. And you can, through the relevant equations, work out the total rate of heat transfer by radiation and convection in the actual environment, in which you have the surfaces which are at at different temperatures and which have different thermal radiation characteristics. If we were to replace that environment by an environment in which all the surfaces are at a constant or a uniform temperature and all those surfaces are black. Now, when I say black, again that refers to a particular type of surface that is defined when you study radiation heat transfer. A black surface is one which is a perfect emitter and a perfect absorber, and no other surface can emit more thermal radiation than a black surface under the same conditions, and any radiation that is incident on the black surface is completely absorbed. So it is none of the radiation will be reflected or transmitted. So if I have the heat transfer rate under actual conditions and I want to replace the enclosure by a black enclosure such that the rate of heat transfer does not remain the same, then that black enclosure must have a certain temperature, and that temperature is known as the operative temperature. Along the same lines, we can define a radiant temperature. In the radiant temperature definition, we only consider the rate of heat transfer by radiation, that is the occupant is exchanging heat in the actual non-uniform environment by radiation, and if I replace that non-uniform environment by a radiantly black enclosure such that the rate of heat transfer by radiation is still the same as in the actual environment, then what should be the uniform temperature of the black enclosure? That would be called the radiant temperature. If of course we deviate from these standard conditions at which standard 55 has been obtained, if you refer to the Ashrae handbook, you are given certain guidelines how you can shift the conditions of the comfort zones. If you increase for example, what happens if the air speed changes, or if people are wearing clothing which has a CLO value other than 1 or 0.5, or if the activity level is greater than 1.1. So there are certain recommendations for those, and if you are interested, you can refer to the Ashrae Fundamentals Handbook to get a more detailed idea of how things would change when we deviate from these standard conditions. Now we will move on to the cooling load. That is our main objective, and take it from over there. So there are certain general steps that we have to go through for estimating the cooling load of a building. The first thing we need are the characteristics of the building, that is the entire building plans, which will give us the various sizes, the building materials, various components, and these will be provided to you by the architect or the firm that is doing the project. We also need the building location, that means the geographic location, whether it's located in Karachi or Islamabad. Then the orientation. When we say orientation, it is whether it's if I look at the north direction, with reference to the north direction, what is the orientation of the building, and so that will also be required when you will see that when we calculate the cooling loads. We might also be interested in external shading. For example, if that building has tall structures or tall buildings in the close by, that will also affect the cooling load. Then we of course need the weather data to select the outdoor conditions, for which I will show you a typical data sheet that I have obtained from the Ashrae Climatic data CD. Then we will select the indoor design conditions based on Ashrae standard 55. We will of course need a schedule of lighting, occupants, and internal equipment and appliances. That when we say schedule of lighting, we will need to know how much is the wattage installed, when do the lights come on, when are they switched off. Similarly, how many people are using that building, when do they come into the building, for how long do they stay inside the building. And similarly for the equipment, what are the types of equipments that are being used, what is their power consumption, what are the times over which those equipments are used, or any other process that causes a thermal load inside the building. Okay, when we want to select the outside design temperature, it is not practical to just focus on the maximum value that you obtained over a period of time. I mean, normally the climatic data that we have is over several years, maybe even 10, 20 or 30 years. So you wouldn't just focus on one maximum temperature that occurred for a few hours at some point and then select or size your cooling equipment based on that temperature as your outside design temperature, because if you do so, your air conditioning plant will be definitely oversized. And if you for most of the year or practically for the entire year, it's possible that your plant will be actually running at a much lower load, and when it runs at a very low load compared to the design load, it's also operating at a very low efficiency, so you will be losing money. So instead of just focusing on one particular maximum temperature, this practice is to select the outdoor design temperature based on what is known as the frequency of occurrence. That is, when we say the frequency of occurrence, we are saying is, let's say if we select the outside design temperature at 4.4% frequency of occurrence, it means that of a total of 8,760 hours in a year, it is possible that 0.4% of the times, that is 35 out of 8,760 hours, the outside temperature may be higher than the temperature that we selected. But 99.6% of the times our plant will give us the desired service in terms of the load that we have. Similarly, we can consider a frequency of occurrence of 1% or 2%. If we select a frequency of occurrence of 2%, it means that in a year it is possible that out of 8,760 hours, only 175 hours are such that our plant is not able to fulfill the load, that the load exceeds the design load. But it is possible, it's not necessary that will happen. And that is the practice. And when we look at the climatic data sheet, you will see that the outside design conditions can be decided upon based on these frequency of occurrence figures of 0.4, 1 and 2%. Another thing that we must also do is to calculate the space cooling load, not at just one time and during 1 month in the year. You will probably go for the hottest month, but you will also calculate the cooling load at different hours of the day, so that you have a correct idea of the peak load that occurs on that day, and against that peak load then you will size or your air conditioning system. You can now see a climatic data sheet for Karachi airport, and it has certain information on it. Of course, we have the latitude, longitude, elevation, standard pressure, the time zone, and the period over which the data has been collected, and based on that period they have developed this climatic data sheet. And there is a identification number for the weather station, So these are identification numbers over here. And then for a person interested in air conditioning, you have the annual heating and humidification conditions and the annual cooling and humidification and enthalpy design conditions. And you can see that for Karachi we are not interested in heating. Had it been, let's say, Islamabad probably, or you might, or Quetta, then heating would also have been taken into consideration. Okay. Now when we talk about the outside design condition, the frequency of occurrence, when you look at the data for annual heating, it's given as 99.6%. that means 99.6% of the time you will be accommodating the heating load, and similarly 99% and 99%. Whereas for the cooling or the summer air conditioning, we have the figures of 0.4%, 1% and 2%. If you look at the first column, that gives us the hottest month. 6 means it's June. And when we look at the cooling dry bulb temperature, that is, if you want to set the outside design temperature at a frequency of occurrence of 0.4%, then it will be 38.9 degrees C. So if I consider my assign a value of outside design temperature to be 38.9 degrees C, then 99.6% of the time I expect that the temperature outside will be either equal to 38.9 or below this, and your plant will be sufficient for that. Only 0.4% of the times you expect the outside temperature might go above 38.9, but it's not necessary. Similarly, if I select a 1% frequency of occurrence, I will have an outside design temperature of 37.2, and for a 2% degree of frequency of occurrence, you will have an outside design temperature of 36. Of course, we can see that if I go for a 0.4% frequency of occurrence, I will have a larger air conditioning size or load, because the outside design temperature is higher, but I will be fulfilling the needs of the air conditioning for 99.6% of the times. So if I am willing to sacrifice a little in terms of the outside design temperature, or the outside temperature exceeding the design temperature, I can opt for an outside design temperature of 37.2 degrees, which will mean that I have a smaller size compared to the previous case, the smaller size of the air conditioning plant. And similarly, it will be the air conditioning plant capacity will be further reduced if I consider an outside design temperature of 36 degrees based on a 2% frequency of occurrence. This climatic data sheet also contains various other data which could be of interest for others. For example, rainfalls and etc., the wind directions, the wind speed. Quite a few of these that information is given over here, and all the short form abbreviations given over here are explained, or on the next page what they refer to. So that's what these abbreviations stand for. Now we look at the types of space cooling loads. We can divide the space cooling loads into two broad types. One are the external cooling loads, the other are internal cooling loads. External cooling loads, if we start by looking at those, one is the heat gain from exterior surfaces. When I say exterior surface, that is any surface which is exposed to direct solar radiation. It can be a roof, or it can be a wall, or maybe one wall, or maybe more than one wall. So any surface that is exposed to direct solar radiation is a exterior surface. A wall can also have a window or windows. It can have a door, so they will also be considered to be exterior surfaces. When we look at surfaces which allow the solar radiation to be transmitted, that is transparent surfaces, which are also known as fenestrations, then there is a second type of load that we have to account for, that is the solar heat gain by transmission. Keep in mind that if when solar radiation or thermal radiation is incident on the surface, there are three things that can happen. Part of it can be reflected, a part of it can be absorbed, and part of it can be transmitted if the surface is not opaque. So when we talk about transparent surfaces, the portion of the incident solar radiation that is transmitted has to be also accounted for separately. There will of course be also conduction through those transparent surfaces. That is, if you have a glass window, that glass has a certain thickness, it has a certain thermal conductivity, and that means there will be conduction across that window pane. So one of the surfaces will be at a different temperature on the outside, that surface on the inside will be at a different temperature, and we can calculate the conductive heat gain as well. Then there are partition walls and interior doors. We have to also calculate the heat gain from partition walls and doors. What it means is that, if I'll just roughly try to explain that, let's say this is the conditioned space, and this conditioned space is being maintained at a temperature of 24 degrees C. And next to this conditioned space we have another room, but this room is not conditioned and it is at a higher temperature. Let's say the temperature over here is 30 degrees C. So what will happen, there will be a heat transfer through this wall or partition between the two rooms, and that is what we mean by heat gain entering from partition walls and interior doors. So there can be a door in this wall as well, there can even be a window between in this partition. So accordingly we can work out the rate of heat transfer through that partition. The partition can also be a basement. For example, if we have a basement over here, and this basement we can consider again is not conditioned, so it is at a temperature, for example, of 27 degrees C, and again there will be heat transfer from the basement into this conditioned space, but this time it will be through the floor of the conditioned space. So this time the floor will also act as a partition. And had this basement, if we had, let's say if this room was not exposed to direct solar radiation over here, but there was another room at the top, and the room at the top, let's say, was not conditioned, then what would happen is that there will be heat transfer through the ceiling of the conditioned space. So then the ceiling would become a partition. And then we come to the fifth type of external cooling load, that is infiltration of outdoor air. When we say use the word infiltration, it is uncontrolled entry of the outside air into the conditioned space. If we are considering summer air conditioning, the outside air will be at a higher temperature. It will also have a higher humidity ratio compared to the conditions inside the space, and when that air enters the conditioned space, it causes an additional load in the space, and that load has two components, sensible as well as latent. Sensible because it has a higher dry bulb temperature, and latent because of its higher humidity ratio. The infiltration can occur, of course, because when doors are opened as people enter the conditioned space and leave the conditioned space, there will be some entry of the outside air into the conditioned space. In addition, the frames of the doors and windows also have small gaps through which this air will enter into the conditioned space. We can try to minimize the effect of infiltration, but it will be there, so we have to keep it in our cooling load estimation. Then we move on to internal cooling loads, and the internal cooling loads are due to three sources: occupancy or people inside the conditioned space, the operation of electrically operated lights, and also equipment and appliances. People are a source of both latent and sensible load, because we are exchanging heat with the environment by convection and by radiation. Then moisture also is being evaporated from the skin of a person, and when you breathe out, the breath also contains water vapor, so that leads to both a sensible and latent load. Electric lights will cause a sensible load, and equipment and appliances can have a sensible load, and in some cases a sensible as well as latent load. For example, if you have a steam generating machine, that will cause a both sensible and latent load. And these loads are pictorially shown to us as well, and you can see over here the various loads that we had talked about that are shown over here. And if we just look at the bottom, there is an additional mention of another load, that is ventilation load. When we say system heat gains, we are talking about the space cooling load, or the heat gain into the conditioned space. You have the exterior loads from exposed, if it is an exposed roof or exposed wall, fenestrations, conduction that is through the walls and windows, transmission through windows, and conduction through the roof, infiltration. And inside we have the three sources of load: the occupancy, electrical lighting, and equipment and appliances. Ventilation is something that we do intentionally. When we were looking at the schematic representations of heating and cooling cycles, if you recall, we were using the outside air, part of it, to be mixed with the recirculated air, and the purpose of that is to maintain the desired indoor air quality, and that is what ventilation is. So ventilation is something that we do intentionally to maintain the desired indoor air quality. But when we bring the outside air, we have to cool it to the supply conditions. That means there is an additional load on the cooling equipment. So once we have calculated the space cooling load, we also need to add the ventilation load to it, so that we can have a better idea of the total load that has to be taken up by the cooling equipment. There are various methods that have been developed over a number of years to estimate or calculate the cooling load. We are only going to work with a particular method that is known as the CLTD CLF method, which is the method described in your book, although this method has been superseded by what is known as the CLTD CLF SCL method. Both are methods which can be used or to calculate the cooling load manually. However, modern day softwares for calculating cooling loads rely or use a different cooling load estimation method, that is the heat balance method, for example, but that requires the solution of a large number of equations in an iterative manner, and that is suitable for computer-based solution. Manually, the method that we are going to go through is the CLTD CLF cooling load method. The CLTD stands for cooling load temperature difference, whereas CLF stands for cooling load factor. And what is the significance of these two terms? That's something that we now need to look at. If you were calculating the heat transfer from outside a conditioned space to the inside, assuming the outside air is at a higher temperature and inside the temperature is lower, we can use an equation from heat transfer, that is Q is equal to UA delta T, where U is the overall heat transfer coefficient, A is the heat transfer area through which the heat transfer is taking place, and delta T is the difference between the outside and inside temperatures. However, when we look at the cooling load on a building, we have to also keep in mind that the outside temperature does not remain constant during the day. It constantly changes. In addition to that, the amount of solar radiation that is incident on a surface also does not remain constant. It is also dependent on a number of factors. That means it will vary. Even if you are at a same location, it will vary during various times of the day. There will be a variation during the year. There will be a yearly variation, daily variation, hourly variation. In addition, there will be a variation of the incident solar radiation depending on the latitude. That means if at 9 a.m. you have a building in Karachi, and if you have a building exactly same like that in Lahore at 9 a.m., the radiation incident will be different because the latitudes are different. So we have, and in addition to all those, the type of construction. If you have a wall, the wall can be constructed of, let's say, concrete blocks. A wall can be made from layers of other materials. They can be wooden sheets or inserted over there. You can also have hollow concrete blocks. So you can have different types of constructions, and when we have a different type of construction, it also affects the amount of heat that is stored in that structure, and that will also affect the rate of the heat transfer through that surface. So if we want to take into account all these variables and still use an equation like we had done in the case of heat transfer, that is Q is equal to UA delta T, we do not, or we cannot use delta T. Instead, we replace delta T by CLTD. So the complex mathematics that is required to produce that cooling load temperature difference value, that is not something we are going to go into it. We will simply use the CLTD factors or values that are given to us in the form of tables. And once we have the table in front of us, you will see how we can select the right CLTD value from the table and then proceed with the calculation of the solar heat gain through that surface. So these CLTD values will be used when you are talking about the solar heat gain through exterior surfaces on which direct solar radiation is incident. So that those could be walls or those could be roofs. Then we have the cooling load factor. The cooling load factor accounts for the fact that the solar radiation that enters the conditioned space, it may be the solar radiation that is entering through transparent surfaces, or it may be the solar radiation that is emitted by any source inside the conditioned space, lights, occupancy, or appliances. And that's thermal radiation that is entering the conditioned space does not become part of the cooling load immediately, because the air is transparent to thermal radiation. So that thermal radiation that enters the conditioned space does not heat up the air instantly. First it is absorbed inside and raises the temperature of the surfaces, then that heat that is absorbed is convected away by the air. So there is a sort of a time lag, and to account for that factor we need the cooling load factor. And again, the cooling load factor will be found from tables that we have for occupancy, for example, and for lights. Now we move on to the actual equations that are used to calculate the cooling loads, and we will look at those equations one by one, starting with the roofs and walls. The equation that we will be using is, as I said, instead of Q is equal to UA delta T, we will be using the equation Q is equal to UA CLTD, and not only CLTD, but you can see it has a subscript ADJ. ADJ is short form for adjusted. When we look at the tables to read the value of CLTD, the tables numbers are given, and we will go through an example in which I will show you how to use those tables. For the time being, we'll just go through the equations and the process of using those equations. So for a particular roof or a wall, the U value will be given to us, or we can find it ourselves if we know the construction of that particular roof or a wall. A will be the surface area through which heat transfer takes place. That can also be obtained from the plans of the building. Then the CLTD value will be obtained from a table, but that CLTD value that is given in the table is for a particular set of inside temperature and an average outside temperature. But that is not necessary that our design temperature inside the conditioned space and the average temperature where we are calculating the cooling load is the same as the reference values in the table. And to account for those variations, we use the value CLTD adjusted, and the formula for CLTD adjusted is also shown over here, and you don't have to remember this formula. When you use the table, you will see that this formula is also given at the bottom of the table. All you have to do is read the value of CLTD from the table. You will know the value of the inside design temperature Ti and the average outdoor temperature T average, and then you can calculate the value of CLTD and adjusted. And once you have got CLTD adjusted, you can calculate the rate at which heat is transferred through the roof or a wall. The next heat gain is conduction and radiation through transparent surfaces. When you calculate the conduction through a transparent surface, for example a window, then the conductive heat gain is calculated using the standard heat transfer equation, that is Q is equal to UA delta T, where delta T is the temperature difference between the outside design temperature and the inside design temperature. The other component, that is the solar gain, that is the energy that is transmitted through the transparent surface, is calculated by using the equation which is Q dot Sg stands for solar gain, SHGF maximum, which is the maximum solar heat gain factor, which is obtained from tables. Similarly, SC shading coefficient is obtained from a separate table, and CLF will be required because we are talking about the thermal radiation entering the conditioned space, and A is the area of the surface through which the heat gain is taking place. That is, the first three factors are obtained from tables, and the total rate of heat transfer through this transparent surface will be the sum of the conductive heat gain and the solar gain. The cooling load from partitions, ceilings or floors, I told you that ceilings and floors can also act as partitions depending on the construction. And to calculate the rate of heat gain through partitions, again the standard heat transfer equation is used, that is Q is equal to UA delta T, and this time delta T is TA, that means the temperature in the adjacent space. It could be a room, it could be a basement, as I said, it could also be a room on the upper level. And we are assuming that because it's a heat gain, the temperature in the adjacent space is higher than the temperature inside the conditioned space. We now come to the internal cooling loads. One is the load due to occupancy or people inside the conditioned space. I told you earlier that occupancy causes both sensible and latent heat gain, and what we will find out is that the sensible heat gain per person, depending on that activity that person is engaged in, that value will be given to us, or we will read it from a table multiplied by the total number of people. And if it's a sensible heat gain, we also have to also multiply it by the cooling load factor, because we are also emitting thermal radiation, and that has to be accounted for by using a CLF. The latent heat gain per person is directly multiplied by the number of persons in the conditioned space, and the total load due to occupancy will be the sum of the sensible and latent heat gains. For the case of lights, because again there is thermal radiation that is emitted from lights, remember any object above 0 Kelvin emits thermal radiation, so there will be a need for finding out a CLF, which will also be obtained from a table. W Q dot will be equal to W, which is W is the total wattage, FU is the utilization or the usage factor, that is what fraction of the total installed capacity are we using. For example, if we have lights which have a total wattage of 4000 watts and we are using 3000 watts out of those 4000 watts, then the usage factor or the utilization factor will be 3 by 4 or 0.75. If it is not given to us, we will assume that all the lights are being used and the utilization factor value will be taken to be 1 by default if it is not given to us. FB is the ballast factor, and that is for light fixtures in which you have any additional component which produces extra thermal load, and if again that is not given to us, we will use a FB value of 1.0. You would have seen that if we look at the old tube lights that we have, there is what we call a choke or a ballast just behind the tube light, and that is also emitting or causing thermal load in the conditioned space. So that is what we mean by the ballast factor, and for light fixtures this value is provided by the manufacturers. For appliances and equipment, again, because we have a if the appliance is only generating a sensible load, then we multiply the wattage by the cooling load factor, and if it has a sensible latent load, then we add that latent load to the sensible load, and the cooling load factor again will be obtained from a table. Infiltration, as I told you, is the uncontrolled entrance of the outside air into the conditioned space, and the method that we will use to calculate the rate at which the air enters the conditioned space is known as the air change method. ACH stands for number of air changes per hour multiplied by the gross space volume in meter cube, and you divide it by 3600 to give you the rate at which the infiltration takes place in cubic meters per second. The idea of number of air changes is that, for example, if we have a conditioned space whose total volume is 100 cubic meters, and if we measure the amount of infiltration in 1 hour and it comes out to be 50 cubic meters, that means the number of air changes per hour will be 50 by 100, that is 0.5 ACH. or that means ACH value will be 0.5, and to convert that into meter cube per second, you will divide it by 3600. Once we have got the value of the infiltration rate in meter cube per second, then we can calculate the load due to infiltration. Remember, there will be a sensible load as well as a latent load by the equations given to us. And you can see that in these equations, the volume flow rate that is used is in liters per second. So make sure the volume flow rate that you calculate using the air change method in meter cube per second is converted into liters per second, and then you can calculate the infiltration load, the sensible and the latent both. And in these equations, T naught and Ti again are the outside and inside air temperatures, W naught and Wi are the outside and inside humidity ratios, which you can read from the psychrometric chart given the inside and outside design conditions. And finally, ventilation. Ventilation is again calculated by using the same equations that we have for calculating the load due to infiltration. This time, however, the volume flow rate due to ventilation will be different, and that volume flow rate will depend on the type of activity inside the conditioned space and other factors inside the conditioned space. Usually these values are given to us in tables, or they will be given to us directly, that for example the ventilation requirement is so much, and we will use those. Otherwise there are tables that you can refer to, and a simple table is given, I think, in this in our book as well, and if required we will use that table to calculate the amount of ventilation air. Now that we have all the equations and the procedure for calculating the various loads inside a conditioned space, we will go through an example in which we will use these equations, and also you will learn to use the tables that are needed to calculate the various loads.